Hello, this is video 54. I'm going to be talking about rotational motion. This is a new topic. We've been talking about linear motion and circular motion, and now we have moved on to rotational motion. So I'd like to start this topic off with a question. So it says, which part of the turntable moves faster? The outer part where the ladybug sits, or a part near the orange center? So when I asked this question in class, the class is always divided. Some people think that she moves faster the outer part, and a very small number think that it's a part near the center, but that's not a possibility. But usually about half the class thinks, well, she's actually moving at the same speed. So it actually turns out that the answer is it depends. I know that's kind of tricky, and I don't ask tricky questions like that on the test, but the point is just to introduce the topic that what do you mean by moving faster? What kind of speed are you talking about? Are you talking about linear speed like we've been talking about? If so, then she definitely does move faster on the outer part because she's covering more distance. She's covering that whole big circle on the outer part while she's only covering a smaller distance toward the center and the same amount of time. So she's definitely moving faster linearly on the outer part. But if we're talking about rotational speed or angular speed, then she's actually moving at the same angular speed no matter where she is on that turntable. So that's why the answer is it depends. It depends what you mean by speed. So from now on, we're going to specify. If we just say speed, then we're usually going to mean linear speed, but we're going to try to be explicit and say linear speed. And if we're talking about angular speed, then we have to say angular speed. So the angular speed is talking about what angle does she travel through, how many revolutions. And you can see when this turns, she's always traveling the same number of revolutions in the same amount of time. So I have a note here that we're going to see again. I just like to introduce it at the beginning, that every point on a rotating object has the same angular motion, but does not have the same linear motion. So we're going to see in this video that there's going to be some relationships between angular motions and linear motion. Actually, we'll see that in the next video. But while we're talking about angular motion, you might be thinking, well, why are we even talking about this? What's the point? And this is the point, that if you're talking about angular quantities, then you just have to use one number to represent the speed, for example, of this ladybug. If you're talking about linear quantities, then when you're talking about the speed of this ladybug, then you have to say where she is, because otherwise you'd have to have an infinite number of speeds to represent the speed here, because it depends on the location. So let's get started. So what we're going to be doing in this video is talking about everything that we've talked about before, the linear quantities, but now they're going to become rotational quantities or angular quantities. So when we first talked about motion, the first quantity we discussed was a distance or displacement. So now we're going to be talking about an angle. When an object is rotating about an axis here, so this middle point is fixed, then this thing is rotating, let's say counterclockwise, then it's moving through a certain angle. So we're going to use that as our displacement. It's called angular displacement, or it's also called a rotation angle. So we're going to use theta. And it turns out that there's a relationship between this angle theta and the arc length. So the arc length is this letter S here. So that's the linear distance corresponding to the angle. And the radius of curvature, you can think of that as the radius of the circle. So the angle that we rotate is equal to the arc length over the radius. The reason that this is important is because it helps us understand the units for the rotation angle, which is the radian, which is abbreviated RAD, and I'll talk about it more on the next slide. So from now on, when we're talking about angular motion or rotational motion, we don't have left, right, up, and down. We either have counterclockwise motion or we have clockwise motion. So we have to use a new sign convention, and we're going to use it throughout this chapter. that if we are undergoing counterclockwise motion, it's going to be called a positive number, so a positive angle. If we're clockwise motion, it's going to be a negative angle. And this agrees with the vector notation that we have used in the past when we're talking about the angles. So now we're ready to just spend a tiny bit more time on the units for the angle, which is the radian, just because this is kind of a funny unit. So I have a slide here, understanding the radian. So the radian is a unit for the angle. And we saw this definition on the previous slide, that the angle is the arc length over the radius. So the way that I like to understand the radian is I like to think, okay, what if the angle that I'm rotating through is a whole revolution? Well, that means that the arc length, that distance traveled, that linear distance here, is the whole circumference of the circle, which is equal to 2 pi r. When you divide 2 pi r by the radius, the radii cancel out here, and you get 2 pi. And that's where the unit of the radian comes from. So this is going to be called 2 pi radians. And this angle of 2 pi radian corresponds to a full revolution. So now we are ready to convert between radians to other units. So let's say that you're told that your wheel is rotating a full revolution. Well, now you can say, okay, well, a full revolution, then that's going to be called 2 pi radians. And you also know that a full revolution is 360 degrees. So there's also that conversion. So it turns out that if you divide by, if you divide 360 by 2 pi to get a radian by itself, you actually get 57.3. For some reason, this number is incorrect. 57.3 degrees. I don't usually use this conversion here because I don't remember it, but I always remember that either 2 pi radians is 360 degrees, or even that pi radian is 180 degrees. If you do half a revolution from here to here, that's half a revolution. Well, that's 180 degrees, and I just use that as my conversion factor. So that's all about the angle. I'm going to stop the video and do part B in the next video.